Hey everyone, a very happy Tuesday and welcome back. It's another ARM Tech Talk. It's so great you could join us, whether it's your morning, your afternoon, your evening. Welcome back to our ARM Tech Talk series for all of the latest trends, technologies, and best practices from ARM and our ecosystem partners. So great you could join us today. We've got an awesome ARM Tech Talk lined up from Bill at Corellium. He's going to be deep diving into some really exciting work they've been doing with virtual prototyping that follows on from a very exciting automotive launch that ARM did a couple of weeks ago. So I'm going to get those slides up right away because we want to get, of course, to the meat of today's topic. He's got a really in-depth presentation, lots of great technical content. And of course, it wouldn't be an ARM Tech Talk without a demo, right? So we're going to see a live demo of ARM Virtual Hardware and the prototyping solution they've got in action. But before we get to that, as usual, I do have a couple of little housekeeping items I'd love to go through before we get to today's presentation. So Bill, if you wouldn't mind just clicking through to the next slide, that would be great. So of course, if you've joined one of these ARM Tech Talks before, you know the drill. We hold these regularly. If you want to engage with us on social media in any way, use the hashtag #OnARM. We've done, I think this could be the 100th Tech Talk, or we're certainly very close to it. We've done pretty much 100 of these now, which is just awesome. This is the best way to discover the latest and greatest from ARM partners in the ecosystem, building the future on ARM. So check out the YouTube link, youtube.com/ARM for all of those recordings. And that includes a really great playlist as well that we've taken from Mobile World Congress. We were live at Mobile World Congress earlier in February. And as a little sneak peek, we're going to be live at Embedded World next week. So if you want to find out more about that and what's coming up there, head to arm.com/tech talks and make sure you're also subscribed to our YouTube channel so you don't miss any of those. We've got some really exciting content lined up. So Bill, if you want to head to the next slide and we can see a photo of you, I'm now going to bring you onto the stage. So I'm delighted today to be joined by Bill from Corellium, who's going to be giving today's ARM Tech Talk. Before I do hand over to you, Bill, just a quick note to the audience. If you've got any questions at any point that you want to grill Bill on, then we can absolutely get to those at the end. To just ask them in the Q&A box, which is on the menu bar, which is on the right-hand side of your video if you're joining us on the event page. Bill, thank you so much for joining us for today's ARM Tech Talk. I'm super excited for it. Please take it away. Tell us a bit more about what you've been working on.
Thanks so much, Tobias. It's great to be here, and thanks to ARM for inviting me. Want to talk today about auto software. Auto software, of course, is hugely growing in complexity, and it seems to be outpacing the ability of other technologies to keep up with it. There is a productivity gap between the software that's required for the latest and greatest things that want to be done for software-defined vehicles and ADAS, and just how it can be handled in today's technology. I stole this graph from an ARM presentation talking about the same thing. But if there aren't fundamental advances in the technology and how we want to solve these problems, they're just going to create bigger and bigger hill for us to climb out. So I want to talk to you about some of the approaches that we're bringing out and working together with ARM to do here in order to solve the problems of automotive software complexity. And a lot of this involves modernizing development and bringing it to the cloud. Virtual devices can very easily leverage cloud-based flows and methodologies. As soon as you take something and remove the need to have it tied to a physical device and are able to virtualize it, you can now place it in the in the cloud and let it leverage the software methodologies and techniques that have been being used for cloud-based development for quite some time now. You can use APIs to control bringing these things up and down, integrate into modern development flows, and of course you can scale this. The nice thing about the cloud is that it's basically almost a limitless pool of compute resources which you can scale up and down, as and doing so with some of the ARM servers out there now means you can actually do it nice and power efficiently too. And the nice thing about the cloud is also it gives you control over your costs too. When you're not using it, and certainly if you've got the right payment program set up, if you're not using it, you're not paying for it. But when you need to deploy massive amounts, you can roll out more and more compute in here and scale your compute up and down to meet the size of your task. Of course, this also means that you can deploy these devices worldwide. This is important because development is done worldwide, and you oftentimes have development being done round the clock with development teams scattered throughout the world. And doing this tied to physical devices means that it's very difficult to keep everyone in sync with the same device, and shipping around the world involves customs, and the device doesn't show up in the same shape it left. I've certainly run into that problem before. And so having this whole thing done in the cloud, just means that everyone is developing on the same platform at all the time. And if you run into a problem, you can share it with the guys that can solve it very quickly. Finally, virtual devices enable you to shift left, and this, of course, shift left is the big mantra that everyone always says about this, and it's true. Virtual devices can be available years before you have actual silicon. The additional thing that we also do here, though, is we shift it right. And the powerful thing on this is, you want to be able to use these devices even once you have actual silicon. This lets you do things like figure out how you're going to handle over-the-air updates, and basically do regressions against every single possible version without needing to have physical hardware for every single possible version. And although that was a bit of an issue back when we were doing this on boards, when you're talking about cars, now it starts to become a really big problem. Who wants to have a fleet of cars sitting around just to test software on? On this? That gets expensive in a hurry. So, this virtual approach lets you start development well before you have silicon and keep leveraging that investment for years after the devices ship. Of course, I'm not saying anything new here. People have been throwing virtual prototypes at problems of this sort for years. I've been one of them that's been talking about that for, let's just say, a few decades. But virtual prototypes have some traditional barriers in here. They take a long time to develop. And a lot of times, by the time you finally get them developed, they're too late to add value, because, that pre-silicon advantage you thought you had, well, if you spend, years developing your virtual prototype, that pre-silicon advantage is gone. And on top of that, by the time these virtual prototypes oftentimes run too slowly for modern workloads. If you look at the traditional virtual prototype, it can take tens of minutes to boot, sometimes even hours on the more complex workloads out here. In addition, virtual prototypes will oftentimes take shortcuts in here. And these shortcuts are done in the name of either, developing faster or running faster. But it means that a lot of times you're no longer testing the same code as you're, as you're going to be using in the physical device. Or your peripheral model is done too simply. So your driver code there is going to execute different paths than the real device will have. And couple this all with traditional virtual prototypes typically have traditional licensing around here, which means you can be, looking at, license fees and starting at tens of thousands of dollars and going even higher, and this is just for a single license. And this, and oftentimes cloud usage, now comes on top of this. Traditional virtual prototypes have not kept up with the demands of modern software developers. So let's talk a bit about why I'm here today, about the right that Corellium has to play in this space. So Corellium has been around for, 5 or 6 years now, and we are the leading company in mobile phone virtualization. We have the industry's only virtualized models for Apple iOS devices. This includes the latest and greatest. We typically have our phones available concurrently with when Apple does. On here, and we have them out in jailbroken and non-jailbroken form factors. We similarly have Android virtual devices in basically all form factors, supporting the fairly old Android versions back to 7, all the way up to the latest and greatest with 14. And we have the features in there that you really want to have inside of here, such as Bluetooth, camera, microphone, GPS, and other sensors inside of here. And we take these iOS and Android devices, and we target them at the security problem. Obviously, security and vulnerability research are big areas of development right now, and that is where we target these. And the ability to have these devices that are functionally equivalent in pretty much every aspect to the physical equivalents, let them be valuable tools for doing vulnerability research, security research, and basically integration into your entire DevSecOps flow inside of here. Underlying all of this is a hypervisor technology that runs directly on powerful ARM servers. This capability is what gives us the ability to virtualize the behavior of iPhones, but it also gives us the ability to virtualize other ARM type devices as well. So let's talk a bit about that, about this technology. We call our technology CHARM, the Corellium hypervisor for ARM. It is a type 1 hypervisor. And for those of you like me a couple of years ago who don't know their hypervisor types, type 1 hypervisor is one that runs directly on the ARM or directly on the physical hardware, ARM in this case. A type 2 hypervisor is one that actually runs on top of an OS inside of there. In here. So we're a type 1 hypervisor, but we support all the ARM architectures, ARM, X, Neoverse, basically in all the modern variants, V7 through V9, in 32 and 64 bits. So basically any ARM device out there that is, has been released in the past long time is going to be able to be virtualized using this technology. We also map processors one-to-one to the underlying server processors. This actually gives us the ability to scale quite nicely as the design size ramps up and leverage the power of the underlying ARM processor on side of here. Now, when we develop this, we do it so that you run the same binaries as the actual hardware, but also to run the same binary paths too. Basically, what this means is that we don't cut corners when it comes to modeling peripherals. Other technologies will sometimes use VirtIO and technologies like that to, basically use a block level representation of these things and leverage the fact that, Linux supports this. What it means though, is you're now using a different driver when you're running in virtual land than when you run in the actual hardware, which means you're no longer executing those same binary pathways, which could have certain implications for, especially for safety and things like that. The net of this technology, though, is that we are able now to run at speeds that are typically at or above real time. I'm not going to say it's going to be the case in every single thing with every single application, but certainly with all the devices that we have modeled today, we're running at or above real time inside of here. And if you take a look at the right on here, that shows you a bit of our technology stack. At the bottom of this is the ARM hardware, and ARM has done a great job of constantly increasing the speed and applicability of their technology into the server space. So we run natively on ARM servers. On top of that runs CHARM, running at exception level 2. On top of that, at exception level 1 is basically where the hypervisor models its devices. So we've got our own control domain, which is called DOM0. It's a Linux in here, and that's where our devices run as well. So our device models, and I've got the IMX93 and the Raspberry Pi 4 listed here. We've got a bunch of other models as well, and then on top of that, running exception level 0 is basically where all the application code lives. And for most systems, this applies quite well. If you want to run a little more sophisticated system and start nesting hypervisors inside of here, then we have a slightly different technology stack, and I won't get into that with you on this. That now lets you handle that, and even to handle higher exception levels as well for doing things like system ready and such like that. So a few years ago, we started partnering with ARM for what's called ARM Virtual Hardware. Now, ARM Virtual Hardware has a few different variants on it. ARM offers a variant on this based upon their fast model and FVP technology. They use us, however, for their third-party boards category. We have done models now for various different silicon providers inside of here. NXP, ST, Raspberry Pi all have boards on ARM Virtual Hardware, and we've started rolling out ARM systems as well on top of this to basically represent the behavior of ARM subsystems, oftentimes well before they're actually being available in silicon. And this is actually now where we've started to take what we first did with ARM Virtual Hardware in the IoT space and now expand it into the auto realm. Before I talk about what we're doing in auto, let's talk about what ARM's doing in auto, because we're going to be leveraging and running on top of this. So back on March 13th, ARM did it, their auto enhanced IP announcement. They rolled out a huge amount of auto IP in here. And if you look at this, the thing that really stood out to me when they did this is, this is one of ARM's slides, is, IP is only a part of what they rolled out on here. because if you go back to that very first slide I showed you, the software problem is a huge one. And so when they rolled out the auto IP in here, they rolled out the software story along with it, the applications that need to run with it, the middleware and operating systems that run with it, and then of course the virtual prototyping solutions that run here. And we're going to talk about virtual prototyping systems here that leverage this IP and the ISA parity that's coming along with it. And ISA parity was a big message that ARM came out with on this, and it's an important one because it shows how the enhanced auto IP that they're rolling out here is completely compliant with the same ISA or instruction set architecture as what you have running inside the cloud. This means that you leverage the same tool flow, the same processes to develop your software to run in the cloud, and then that same binary can then go out and run on the physical hardware itself. And we're helping ARM extend that and give you ISA parity across all of your compute platforms. So along with this, ARM rolled out this slide as well, and I had to include it. I think every virtual prototype discussion I've done throughout my career has included some variant on this because it's true. A virtual prototype approach lets you parallelize the development of your software, do it in tandem with your hardware design well in advance of silicon availability, and get a head start on here. Sometimes up to 2 years in advance of when you get the real hardware. And this means that you lessen the time for doing that system integration tasks, and of course you lessen the overall time to market. So the last ARM slide I'll steal from their presentation on here. I stole the left-hand side of here, because they rolled out virtual prototyping systems along with this, and they announced some partnerships in here, including a partnership with us, Ampere and AWS in here. To add on top of this, we're rolling out some of our own systems in here as well. The first is Cortex R82 AE systems. We're taking the R82 Automotive enhanced version in here, making it available for folks to develop on in the cloud. This gives you both OS and hypervisor support on here, which means that you can actually develop mixed criticality software entirely in the cloud. And this is available today. You want to log on to avh.arm.com. You can go in and start playing with these systems today. We are also partnering with ARM to roll out a version of the RD1 AE system. And I'll show you what that is here in a minute, because it's a very, very advanced system, leveraging the latest generation ARM IP. But it's also going to have the capability to run the complete SOFI stack in here, the mixed criticality here, to combine the compute subsystem along with safety islands, et cetera, from there. And I'll show you more on this. And this system will then run on Graviton 4 or Ampere 1 systems. And as soon as Graviton 4 comes out in commercial availability, we'll have the corresponding system available to run on this as well. This is our R82 AE system. You can see it's pretty straightforward, but this has all the components you need in order to get up and running with a modern OS or hypervisor up on top of it. I think we have 3 different variants of this that run today on ARM virtual hardware. If you want to get a little more complex, though, this is the RD1 AE system. I borrowed this block diagram from the ARM website, but you see on the left-hand side of here is the primary compute cluster on here, based upon the Neoverse v3 AE that was included in the ARM IP announcement. On top of this, you've got a complete software stack, including system ready IR. You've got Zen as a hypervisor running on top of this. And in this case, we've got a couple of different Linux hosts running inside of this as well. You've got your safety island modeled inside of here using the Cortex R82 AE. In multiple instantiations, we've got 3 safety island clusters on here. And then finally, you've got the RSS, SCP, and LCP, basically different control processors running alongside this as well. You can see it's an extremely complex system here in order to handle all that software complexity that we talked about earlier. And this is what we'll be rolling out, here shortly, when the Graviton 4 becomes commercially available. So we're going to be running a little short on time, and I want to have some time for our demo. So I'm going to skip that slide and talk about how our technology is overcoming some of those virtual prototype barriers that I mentioned earlier. Many of these models are available today, so you're not waiting around for these things to develop. We're constantly working on new models as well, that we're developing ourselves, or we can enable you to develop them yourself using our developer kit. Our devices, as I said, typically run as fast or faster than real devices and boot in seconds. So you're not waiting for tens of minutes or hours for these to boot. We execute the same binary pathways as the real device, meaning that you're testing the same binary pathways, meaning that you've got more confidence that what you've developed in the cloud will actually run on the physical device. And on top of that, we're using a SaaS payment model for these devices. You're not talking about needing to spend tens of thousands of dollars or hundreds of thousands of dollars to use this. You can log on, swipe a credit card, and pay us $1.50 an hour in order to get this. We actually do have free hours when you log in as well, and I'll show you the link for this in a little bit. But first, let's get to a demo on here. We'll have these QR codes available for you in a minute as well. So let's go and actually see ARM Virtual Hardware in action. I'll bring this up over here. And this is ARM Virtual Hardware. As I mentioned, we have the ability to have a bunch of different devices inside of here. So we've got the NXP IMX93, Raspberry Pi 4, some other systems from ARM, the Smart Vision Configuration Kit, R52, R82, NXP IMX8. And so we've got a large number of systems available for you to use entirely in the cloud. But let's talk today about our Raspberry Pi system on here. So let's bring this up. And you'll see that I've already got something running here. Let's stop this for a second on here. But let's go over a few of the functions on here. So we can connect this if we want. In fact, we can SSH into this device and running. And so let's actually do that to run my demo here in a minute. So I'm now connected inside of here. It's a standard Raspberry Pi, so I've logged in with our standard password on here. If I didn't want to use SSH to connect, I could use VPN. We've got a partnership with Remote, so you can use them to log in and manage services as well. We have a core model API to interface to the various transaction APIs on side of here, and also the ability to do things like connect debuggers. If you're developing software in here, you want to be able to debug this, and we let you do that as well. We make the LAN address for this then publicly available, so you can do things like SSH into it, like I just did, or connect to some of the services inside of here. We have the ability to trace any executable running inside of this or thread. You simply select that here. You can use various settings inside of here to load your own kernel, load your own device tree, or use VMMIO, virtual memory mapped IO, to extend the behavior of this. And we'll give you memory mapped IO ports on here that you can attach to over the network and then model the behavior of certain, of your own devices inside of here. Of course, we've got the console that I just logged into and sensors in here. So on the Raspberry Pi, we have the ability to attach to the camera and microphone that are running here on my PC. Other sensors are available on other devices as well. You can see over here actually on this Raspberry Pi screen that we have the Bluetooth over here, because this Raspberry Pi is fully Bluetooth enabled on here also. And finally, we have the ability to create snapshots. We're actually just now introducing also snapshot sharing, which means that you can take a snapshot of your device, say when you encounter a bug, and share that with some other member on your team so that they can then go and help you debug what's going on inside of that. But let's actually go into this, into the demo on here. Let's go into full screen on here so we get a little bigger on here. And let's bring up that demo that I was showing. So what I'm going to show you here is MediaPipe. MediaPipe is a great machine learning framework from Google, and Google uses this themselves to run a lot of their own services on here. It's in Google Photos and etc. from here. There are a lot of great examples on here, and I'm going to show you one here that basically does hand recognition for gestures on here. So if I run that on here, you'll see that it basically takes my camera and feeds it on through. You'll see that it's running at a frames per second of around 30. If you try this on your Raspberry Pi 4 at home, you'll see it runs at a frame rate of around 9 frames per second. So we're running about 3 times faster here on this. And you'll see what we're doing here is we're recognizing hand gestures. And you can see here it's saying that I've got an open palm. I can change to pointing up. I think it'll do the victory sign as well. Thumbs up. So this is great because it actually shows how you can do some inferencing. I didn't have to write a single line of code for this, which is good because my programming skills are suspect anymore on here. But it lets me play around with this. There are other examples that you can use inside of here as well. Another fun one I like is to face. I forget what. Let's do the face landmarker. That's Raspberry Pi inside of there. Let's do the setup on this, and it's going through the setup. Watch me fail this demo, just to go with the thing that every demo should always fail when you try and do it live on here in here. But I think it's did fine. Python, and then let's see, it's detect pi. And now it comes up, and now it's landmarking my face inside of here. Once again, running at 30 frames per second. But you can see when I wink my eyes, raise my eyebrows, and such on here. So it has the ability to take my face, put the landmarks around it, and integrate it in, and do all of your fun machine learning things alongside of it. And once again, I didn't have to write a single line of code for this. It leverages the MediaPipe framework. We've got an entire blog on how to do this and replicate this. This same results yourself, and try out some of what's available on ARM virtual hardware. So with that, let's go back to the presentation on here, and I believe that takes us to the final slide on here. And so there are some QR codes on here to access ARM virtual hardware. As I mentioned, anyone who logs in is immediately granted access to 24 free device hours that you can use over 30 days. There's another QR code on here to replicate what I just did with MediaPipe. It honestly is really that simple on here, and all runs on ARM virtual hardware. Thanks for joining. If you have any questions, please feel free to send me an email, or if you're online, ask them here.
Amazing. Thank you so much, Bill. That was awesome. The demo got shone, and I bet that was nerve-wracking coding live on a live stream talk, remembering all the commands, which order to put them in, etc., making sure there's no typos. You did an awesome demo, some really great job, and really showed off the key benefits of the solution. And thank you for your work supporting our automotive launch a couple of weeks ago, and really showcasing how people can accelerate their automotive development life cycles with this. But that, I believe there's one more thing we want to talk about, right, before we do go to questions.
Indeed.
Would love for you to talk a bit more about what's going on in Embedded World next week. As I say, we're going to be live at Embedded World, bringing some cool innovations from the show. And Embedded World's going to be showing how we're building the future on ARM out there in Nuremberg. So do come to the ARM booth. But I believe you've got a little sneak peek at what's coming.
I do indeed. Yeah. So yes, Corellium is going to be in the ARM booth at Embedded World next week, and helping out with 2 different demos that are showing off of there. There is going to be one done by the IoT group there at ARM, showing off Smart Vision on here, and they're going to be showing off a Smart Vision workload that's tied in with AWS Greengrass on here, and leveraging the services on here to basically demonstrate doing some inferences on camera feeds on here. I think it's actually done with a pre-done video on here instead of the camera feed itself on here, but it's going to show some of that isoperi that I was talking about, because they're going to take the same exact binary, run it on an IMX93 board, and that same binary will also be running on ARM virtual hardware Corellium instance out here. But it'll be showing inferences, capturing them in Greengrass, and then displaying them on a CloudWatch dashboard on here. So that'll be a very good demo being done by our friends at AWS and NXP. Obviously, we'll be there to help. We'll also have an auto demo out there as well. They're going to be showing off a mixed criticality workload on here, basically taking the AutoWare AD capabilities and showing off this running with the compute cluster running on a Neoverse V1, Graviton 3 instance running in the cloud, and then that connecting to the R82AE instance that I was showing out there for the mixed criticality portion on here. So it's a really nice demo showing just how advanced you can get on here and running your mixed criticality workloads, entirely in the cloud.
That's going to be awesome. So please do come along. If you're in Embedded World or think of coming to Embedded World, come along to the ARM booth and come and check out these demos. And thank you to the Corellium team, the AWS team, NXP team, and everyone who's been involved in getting all these demos up. So yeah, super excited to see those live next week. I certainly am. And if you can't attend, do tune into our live ARM Tech Talk series that will be broadcasting from Nuremberg, where we're bringing you all the latest and greatest partner innovations at the show. So subscribe to the YouTube channel. Make sure you don't miss any of those. So it's what an amazing talk, great demo, and I'm sure, and there's questions coming in now. I've got a couple just to kick things off while those come in, but I'd love for you to talk a bit more. You mentioned it in the presentation, right? The announcement we made a few weeks ago about the new automotive enhanced IP, but the importance for and one of the key things you pulled out there, of course, was the virtual prototyping solutions that we announced as well alongside this. We had this really exciting announcement, and thank you for being a part of it. And it's great to follow up with your ARM Tech Talk. I'd love for you to talk a bit more about why is it that you support ARM? Why do you work with ARM and with ARM technology, with ARM boards, with ARM IP, and how are ARM's customers going to benefit from this latest new automotive enhanced IP and the work you're doing to help support this and accelerate the software development life cycles?
That's a great question. It's pretty straightforward. We support ARM because it's the technology to build on. The ability to have an ISA that runs not only in the cloud but at the edge and in the auto device, and to take that same workload and migrate it from one to the other without the need to recompile, et cetera, like there, means that you can leverage ARM's compute capabilities basically wherever you are. So no matter wherever you're developing, you're able to develop and run on ARM. So for us, the ability to take the work that we had done, targeting mobile devices, and now, with a few tweaks, basically say, now we can offer a platform that, has the ability to model, mobile phones, cars, edge devices, basically everything out there, because ARM is pervasive and everywhere. Just basically means that it's a great way to get out there and offer value ourselves in here and be a part of the overall ARM ecosystem.
Amazing. Thank you, Bill. And thank you, as I said, again, for all your work to support this launch and for being an ARM partner. We're super excited to have you do this tech talk today. And again, a really great demo. You talked about the great technology that you've got there. I'd love you to talk a bit more about how does this compare with other technologies out there, like, let's say, QEMU. What are the sort of the differences and that you get from your technology versus that?
That's a great question, and probably one that I get asked almost every time I do a technology presentation on here. Believe it or not.
Damn, I tried to be novel with the question I came up with, but everyone's asking it.
Yeah,
but I'm sure people are interested.
Yeah. So QEMU, stands for Quick Emulator out there, and it's an open source model out there that that models a lot of various ARM devices out there, and it does a great job for the problem that it solves. You can look at it as basically largely a simulator that has the ability to occasionally run as a hypervisor. And I would say we flip that around. We're a hypervisor that has the capability to occasionally run as a simulator inside of here. This gives us the ability to run much faster because we spend most of our time running directly on the underlying ARM hardware. And we have the ability to then jump on top of that and model the other non-ARM IP components in here with good models whenever we need to drop into that. The converse on this, the QEMU will model the peripherals more simply. Like I said, typically uses VirtIO in order to do this, which means you're not getting your binary equivalents. But then when you're running in the ARM processor is when it's able to take advantage of that and start running in like a KVM mode and start running quite a bit faster. Still not as fast as us inside of here. Another key area on top of this is the licensing model that goes along with it. QEMU, as I mentioned, is open source and has LGPL on here, which makes it great to develop with, but it makes it a bit more complex if you're trying to integrate this into your own commercial solution in here. Our stuff as a commercial solution, is much easier to leverage inside of here and integrate into commercial oriented flows. We do, of course, also then work with OSS folks on here though as well, and give pricing advantages and such, because we want to be a good steward of the ARM ecosystem as well.
Thank you, Bill. That's really great to hear, and we've got some questions in from the audience as well. I'd love to get to and love to grill you on. There's some really so let's get to those. What I'll do is I'll bring us back into this view for us to be a bit larger on screen, but we'll keep the slides up and we'll flick back and forth between those. We'll flick back to the slide with the QR codes at the end, so people have a last chance before we wrap up. And this is a question I was actually wanted to ask you as well. So Steph from AWS. Says, awesome talk / demo, Bill. Can you talk a bit more about creating some custom virtual boards if a customer asks to bring up their modified ARM-based board? Is that possible?
Yes, it is, and that's a great question on here. I touched real quickly on here when I talked about CDK, but there are a couple of different ways to extend this. As I mentioned in the talk with Raspberry Pi, we have something called virtual memory mapped I/O, and we have this for almost every device. And so you can take an existing device that's already out there running and basically attach a memory mapped I/O peripheral inside of here. Put whatever functionality you want into here, on here, and then basically have it generate an interrupt when it's done on here, back to the calling system, and then write a driver on here. So you have the ability to basically bring in any peripheral you want. That won't let you do the really complex stuff like modeling your own device. And for this, we have what we call the CHARM developer kit. Remember that CHARM stands for the Corellium hypervisor for ARM. And we have an entire development kit that lets you basically develop the same way our developers do inside of here. It's a device. It has a complete SDK on side of it, a complete set of APIs, and a complete set of source code for peripherals inside of here. So you get to use the building blocks of the stuff that we've already done, integrate it together with your own modeling in here, same modeling APIs that we use when we develop ourselves, and same testing. So you now have the ability to pull together systems that are just as complex as we do on here with your own development. We also partner with the Judge Group. The Judge Group is the ARM Center of Excellence for doing AVH modeling on here, and they're a services organization that we've also trained up on our stuff and equipped with CDKs, and so they have the ability to do development as well, and they've developed some AVH devices also in here, and they're doing this for a few other partner companies. So there are a number of different ways to take advantage of this and add your own devices.
Absolutely, and that's great to hear. I'm sure folks on the call are delighted to hear that. So I'm sure they'll get in touch with you, with Judge, and others to create their own and look at how they can create their own ARM-based devices and accelerate their software development and tests. So thank you again for that, Bill, and thanks, Steph, for the great question that's come in. Let's get to the next one actually as a follow-up from that, which is there then a limit to how many models that can be run at the same time?
Well, it's the cloud, right? So, the nice thing is, you can use our APIs at any point in time, or do it on the GUI if you want, to spin up basically limitless number of devices in here. You're limited only by the number of servers we have running at any point in time, and we try and identify this when we start running low and ramp up more on here. So, we've done training courses with hundreds of devices up and running at any point in time, and there is no scalability limit really on here, or practical on here. So you can scale up virtually limitless numbers of devices in order to meet the size of your computing task.
That's great to hear. Thank you for that, Bill. And we've had a couple more questions come in. One from Varun here, or Varun, apologies, depending on how you pronounce that. How are the automotive SoC devices virtualized, for instance, C models, etc.?
Well, that is how we do it in here. So we use C as our own modeling language in here when we're doing this. If you've got your own peripheral devices or your own models in here. For example, we do this for ARM's NPUs. Instead of reinventing the wheel, we take NPU models from ARM as C models, and we integrate them directly inside of here as well. So we have the ability to take existing models and incorporate them into the systems that we create.
Brilliant. Thank you for that, Bill. And questions come in. Have you considered organizing continuous engineering processes around these virtual prototypes, and how much would it reduce the release cycle?
Well, I've certainly considered it. I don't develop automotive software myself on here, but if you go to our website, support.corellium.com/SDK, you'll get access to our APIs. And this is we have an AVH equivalent as well, which is on the ARM developer website. I don't have that link memorized off the top of my head though, but it's the same APIs. You have access to a rich set of APIs here to let you tie into things like DevOps flows or other development flows out here. So you have the ability to tie into something like maybe a GitHub Actions. So now whenever you do a pull request, you automatically then generate about a validation run against here. Spin up as many devices as needed, do your test, and then return the result back in. So you fully integrate into these existing CI flows. I mean, it's a lot of what I said in my second slide, I think, leveraging the power of cloud-based development flows. And we've got all the APIs in here in order to integrate directly in.
Amazing. Thank you for that, Bill. And just while we wait for one or two more questions to come in before we do wrap up, is there anything, let's just flag up those QR codes again, just because I have had a ping saying, I missed the QR code. Can you flag it up again? So let's get that one, let's get that up. I'll just wait for you to get that screen up, and there we go. So if you missed the QR code, get those up there as well. And the questions come in about, have you considered, or is it possible to look at coupling these models with other simulation models developed in other software packages, for instance, MATLAB?
Yes, and in fact, we're currently working on this in a few different areas. I'm working right now with the folks over at Vector and integrating our stuff in with SILKit, for example, as a nice auto testing framework. On this, our APIs will let you tie in. I touched briefly on this when I talked about some of our transaction level APIs called Core Model in here when I was going through the Raspberry Pi. That gives you transaction level access to basically all of the peripheral interfaces on here. For auto, you've got your things like CAN buses. For things like MATLAB, you oftentimes want to interface to an ADC link or things like that. And we have the ability to tie directly into those, GPIO, et cetera, and do that. So, our API will tie very well into pretty much any other simulator flow like that.
Brilliant. Thanks for that answer, Bill. And I guess just before we get to one or two more questions as they come in and wrap up, is there anything else you'd like to add? I know you covered a hell of a lot in that presentation, but I guess based off the questions that come in, or is there anything else you'd like to add for the audience today before we have one more last question?
Well, we touched on Embedded World. I'm going to be there next week together with a few other Corellium folks, largely around the ARM booth, but I'll be around the floor as well. Would love to chat with anyone that may be around, discuss any questions or how we can solve any problems that you may have.
Amazing. Thank you for that, Bill. And I guess, if there's one last question, we'll give it a moment for it to come in. But no, really appreciate you doing this ARM Tech Today. Thank you so much for doing that. I guess, where do you see the kind of future of automotive development going with this kind of, be great to pick your brains on this and get your perspective on this. Where do you see the kind of future of automotive development going with the work you're doing and the partnership with ARM and the industry as a whole? Where do you see things going? As you look ahead, what excites you the most?
Well, I mean, the potential of this and the whole isoparity thing, the ability to develop in the cloud, which is where most modern software development is doing, take that same workload and carry it seamlessly over to its automotive equivalent, since you can run basically the same processor with automotive enhancements out there, and leverage the investment that ARM has done in establishing that isoparity. That to me is the exciting thing, and the ability to take all of this, do it in the cloud, and out there. And of course, we play a role in this as well, and then being able to virtualize the devices themselves, and do things like mixed criticality, since the servers only represent one of the 3 different ARM server types, so you need the ability to virtualize the others.
Amazing. Thank you so much, Bill. Yeah, it's really exciting to see what the future holds and how it's going to be built on ARM. And I think we're really just at the start here. So thank you for highlighting the great work you're doing and the great partnership you have with ARM, and the incredible abilities you have, as you say, with that ISA parity and the CloudSwitch story that we can tell together is fantastic. So thank you for that. Thank you for a great presentation. And audience, thank you for some really, really great questions. If you've got any more, Bill, I'm sure you're happy for them to follow up with you directly, LinkedIn, email, whatever it is. So please do follow up with Bill and the team. Do come and check out our demos at Embedded World at our booth next week. We're going to be there from Tuesday through Thursday in Nuremberg. So do come and check it out. There's a dedicated arm.com Embedded World webpage. So do go and check that out as well, where you'll find out all of what we've got coming up. Some really exciting lightning talks, which are on the booth itself, as well as ARM Tech Talks Live, which will bring the show to you wherever you're joining us from. So do make sure if you're going to the show, you come along and register for the lightning talks. And if you're not able to, do register for the ARM Tech Talks and just press a little reminder icon on YouTube, and you'll be reminded when we go live. So all that remains for me to say is, Bill, thank you so much for a great presentation. Audience, thank you again for some amazing, really, really great questions. And we look forward to seeing you next week at Embedded World for for loads of ARM Tech Talks, as we bring the show to you and show really how Embedded World, and indeed the future of AI, and indeed the future as a whole, is being built on ARM. Bill, thank you so much again.
Thanks, Tobias. Thanks for everyone for joining.
Thanks so much, everyone. Bye-bye.